There is a planet hanging in our sky that we have almost completely abandoned. Venus, our closest planetary neighbor. A world so similar to Earth's composition that scientists once called it our twin. But we haven't sent a dedicated American spacecraft to Venus in more than 30 years. The last time NASA put a probe in orbit around that world, the year was 1989. That mission was called Magellan, and when it arrived at Venus, it revealed something extraordinary. Magellan mapped a world covered in volcanoes, lava plains, and towering mountains, a surface that appeared geologically young and utterly alien. The data from Magellan raised fundamental questions about what makes a world capable of supporting life, questions that remain unanswered to this day. And yet, for 3 decades, we turned away. While Mars received mission after mission, Venus remained in the shadows, a world of intense scientific importance that somehow became planetary science's overlooked stepchild. This is the story of why we abandoned Venus and why we're finally going back. The Magellan spacecraft was built from spare parts left over from other programs. Its radar system came from Voyager. Its propulsion module came from Mariner. Its star scanner came from Galileo. Magellan was a mission born of budgetary constraints and political compromise. But it was spectacularly successful. After a 15-month cruise, Magellan entered orbit around Venus in August 1990. For the next 4 years, its synthetic aperture radar penetrated the planet's clouds and mapped the surface in unprecedented detail. Resolution down to about 300 feet per pixel, coverage of more than 98% of the planet. What Magellan revealed changed our understanding of Venus entirely. The surface is covered in volcanic features, massive shield volcanoes, some larger than anything on Earth, vast lava plains that stretch for thousands of miles, pancake domes where viscous lava oozed out and solidified into bizarre flat-topped mountains, coronae, circular features created by mantle upwellings that deformed the crust from below. The planet appears geologically young. There are fewer than 1,000 impact craters on the entire surface. For comparison, Earth's moon has millions. Mars has hundreds of thousands. Venus's low crater count suggests that the surface was completely resurfaced sometime in the past few 100 million years. This was unexpected. Scientists had assumed Venus would be geologically dead. With no tectonic plate movement and no water to lubricate crustal motion, the planet should have frozen into a static state billions of years ago. Instead, Magellan found evidence of relatively recent volcanic activity, perhaps even ongoing volcanism. The tesserae were particularly intriguing. These are highland regions, continent-like plateaus that rise above the volcanic plains. They have complex, folded structures that suggest intense deformation. Some scientists believe the tesserae are ancient crustal material, the oldest rocks on Venus, remnants of whatever existed before the global resurfacing event. If that's true, then the tesserae might preserve evidence of Venus's past, a time when the planet had a different climate, perhaps even liquid water on the surface, but we don't know. The resolution of Magellan's radar wasn't good enough to definitively determine what the tesserae are made of, and no mission since has provided better data. Magellan operated until October 1994. At the end of its mission, NASA commanded the spacecraft to dip into the upper atmosphere, where it burned up and fell into the clouds below. After Magellan, the United States sent no more dedicated missions to Venus. In August 1996, a team of scientists announced that they had found microscopic fossils in a Martian meteorite called ALH 84001. The rock had been blasted off Mars millions of years ago by an asteroid impact, traveled through space, and eventually landed in Antarctica, where it was recovered in 1984. Inside the meteorite were tiny structures that looked, to some researchers, like fossilized bacteria. The announcement made global headlines. NASA immediately began planning new Mars missions to search for additional evidence of past or present life. The claim didn't hold up. Further analysis showed that the structures could have formed through purely geological processes. They weren't necessarily biological at all, but the damage was done, or rather, the momentum was established. Mars became NASA's primary target for planetary exploration. Mission after mission was designed and launched: Mars Pathfinder and its Sojourner rover in 1997, Mars Global Surveyor, also in 1997, Mars 2020, Perseverance rover, and Ingenuity helicopter in 2020. This list doesn't include the missions from other space agencies: Europe's Mars Express, India's Magellan, China's Tianwen-1 orbiter, and Zhurong rover. Mars became the center of planetary science. Everything flowed toward the red planet. Venus was left behind. Part of this was practical. Mars is easier to explore. Its atmosphere is thin, making landing relatively straightforward. The surface temperature is cold but manageable. Rovers can survive for years, even decades. Solar panels work. Electronics don't need special thermal protection. Communication is reliable. Venus, by contrast, destroys everything. The longest any lander has survived on the surface is just over 2 hours. The extreme heat, pressure, and corrosive atmosphere make conventional exploration nearly impossible. You can't use solar panels. Electronics fail rapidly. Even specially hardened components succumb to the environment within minutes or hours. From an engineering standpoint, Mars makes sense as a target. But science is supposed to be about answering the most important questions, not just the easiest ones. And Venus has profound questions to answer. Why is Venus the way it is? That's the fundamental mystery. The question that matters not just for understanding our neighbor, but for understanding Earth itself. For understanding what makes a planet habitable. For understanding what happens when a world transforms from a potential paradise into a hellish wasteland. Because Venus wasn't always like this. The evidence comes from the atmosphere. Specifically, from the ratio of heavy water to normal water. Heavy water is H2O, where one of the hydrogen atoms has been replaced with deuterium, a heavier isotope of hydrogen that contains an extra neutron. Deuterium is harder to lose to space because it's heavier. Normal hydrogen escapes more easily. Venus's atmosphere has a much higher ratio of heavy water than Earth's, about 150 times higher. This suggests that Venus once had far more water than it does now. The normal hydrogen escaped to space over billions of years, leaving behind the heavier deuterium in a gradually concentrating residue. How much water? Possibly enough to cover the planet in oceans. If Venus once had oceans, it must have once had a climate capable of sustaining liquid water. Temperatures between 0 and 100 degrees Celsius. An atmosphere that wasn't dominated by carbon dioxide. Clouds that weren't made of sulfuric acid. In other words, Venus may have once been Earth-like. What happened? How did a potentially habitable world transform into the hottest planet in the solar system? The answer involves something called the runaway greenhouse effect. Here's how it works. Venus receives more sunlight than Earth because it's closer to the Sunday, but early in the solar system's history, the sun was dimmer, about 30% less luminous than it is today. So early Venus might have had temperatures similar to Earth. But as the sun gradually brightened, Venus began to warm. Water evaporated from the oceans into the atmosphere. Water vapor is a greenhouse gas. It traps heat. So, as more water entered the atmosphere, temperatures rose further, causing even more water to evaporate. This is a positive feedback loop. More heat leads to more water vapor, which leads to more heat, which leads to more water vapor. The cycle continues until all the water is in the atmosphere, creating an incredibly dense, hot blanket of steam that traps solar energy. At that point, Venus would have had an atmosphere thick with water vapor. Ultraviolet light from the sun splits water molecules apart into hydrogen and oxygen. The hydrogen is light enough to escape to space. The oxygen reacts with surface rocks or combines with other atmospheric compounds. Over hundreds of millions of years, all the water is lost, first to the atmosphere, then to space, leaving behind a desiccated world. Meanwhile, carbon dioxide builds up. On Earth, carbon dioxide is removed from the atmosphere through weathering and plate tectonics. Rain combines with atmospheric carbon dioxide to form weak carbonic acid, which reacts with surface rocks. Those carbon-bearing minerals are eventually subducted into the mantle at tectonic plate boundaries, removing the carbon from circulation. But this process requires liquid water. Without water, there's no weathering. Without weathering, carbon dioxide accumulates. Volcanic outgassing releases carbon dioxide faster than any other process can remove it. So Venus ends up with an atmosphere that's 96% carbon dioxide. A greenhouse effect so extreme that surface temperatures exceed 450 degrees Celsius. Hot enough to melt lead, zinc, and tin. This is the scenario that most scientists believe explains Venus. But there's uncertainty in the details. When did the runaway greenhouse effect begin? Was it early in Venus's history? Or did the planet remain habitable for billions of years? Did Venus ever actually have oceans? Or was it steamy and hostile from the start? These questions matter because they affect how we think about habitability throughout the universe. Exoplanet surveys have found thousands of planets orbiting other stars. Many of them are Earth-sized or Venus-sized. Many orbit in what's called the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planetary surface. But we can't actually see the surfaces of these worlds. We can only measure their sizes, masses, and orbits. We can sometimes detect atmospheric compositions, but only for the brightest, most easily observable examples. How do we know if an exoplanet is more like Earth or more like Venus? How do we distinguish between a habitable world and a hellish one? Right now, we can't, because we don't fully understand what separates Earth from Venus. We don't know what tipping points exist in planetary climate evolution. We don't know what signs to look for that indicate a planet has passed the point of no return. Venus is the key. Studying our neighbor can teach us how to interpret observations of distant worlds. It can tell us how common Earth-like planets are. It can tell us whether habitability is rare or abundant in the galaxy. And we've been ignoring it for 30 years. In September 2020, an international team of scientists announced that they had detected phosphine in the clouds of Venus. The detection came from two telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. Both observed a spectral signature at 1.1 millimeters wavelength that matched phosphine gas. The announcement sparked immediate controversy, not because phosphine itself is unusual, but because of where it was found and what it might mean. On Earth, phosphine is produced almost exclusively by life, specifically by anaerobic bacteria living in oxygen-depleted environments. The digestive tracts of animals, microbes create phosphine through metabolic processes that we still don't fully understand. There are no known abiotic processes that produce phosphine in significant quantities on Earth. Not volcanism, not lightning, not atmospheric chemistry. Life is the only substantial source. So, finding phosphine on Venus raised an uncomfortable question. Could there be life in the clouds? The idea isn't as absurd as it sounds. The surface of Venus is hostile to any life we can imagine, but 50 kilometers above the surface, conditions are different. The atmospheric pressure matches that at Earth's sea level. Temperatures range from about 20 to 30 degrees Celsius. Water droplets exist, though they're mixed with sulfuric acid to form concentrated acid clouds. Some scientists have speculated that microbial life could survive in those conditions, protected inside liquid droplets, using sulfur chemistry to extract energy, floating in the clouds indefinitely, carried by atmospheric winds. It's an extraordinary claim, one that requires extraordinary evidence, and almost immediately, that evidence began to crumble. Other researchers reanalyzed the telescope data and found problems, processing errors, statistical uncertainties, potential contamination from sulfur dioxide, which has a similar spectral signature to phosphine. Some analyses concluded that there was no phosphine at all. Others suggested that the amount detected was much smaller than originally claimed. Additional observations using different telescopes failed to find phosphine. NASA's Sophia Airborne Observatory saw nothing. The Infrared Telescope facility in Hawaii saw nothing. Data from Europe's Venus Express spacecraft, which orbited the planet from 2006 to 2014, showed no signs of phosphine. The scientific community split. Some maintained that phosphine was real and required explanation. Others argued that the detection was flawed and the entire claim should be dismissed. Then, in 2024, new observations from the James Clerk Maxwell telescope detected phosphine again. This time with more data, better signal-to-noise ratios, and improved analysis techniques. The team announced preliminary findings indicating not only phosphine, but also ammonia in the clouds. Ammonia is another gas that shouldn't exist in Venus's oxidizing atmosphere. Like phosphine, it would be destroyed rapidly by photochemistry. And like phosphine, it's primarily produced by life on Earth. But ammonia has an interesting property. When dissolved in sulfuric acid, it acts as a buffer. It reduces the acidity. If there were microbes living in the acid cloud droplets, producing ammonia would make their environment more survivable. It would be a form of environmental regulation, creating a habitable niche through metabolic byproducts. This doesn't prove life exists on Venus, not even close. But it does suggest that something strange is happening in those clouds, something that current atmospheric models don't explain. Several hypotheses have been proposed. Volcanic outgassing of phosphides, mineral compounds containing phosphorus in a reduced state, photochemical reactions on dust particle surfaces, lightning-driven chemistry, exotic atmospheric processes that we haven't considered because we've never seen them before. None of these explanations are fully satisfactory. Volcanism would require enormous volumes of unusual magma composition. Photochemistry models can't produce enough phosphine to match observations. Lightning on Venus, if it exists at all, is rare and weak. The most honest answer is that we don't know. We don't understand Venus's atmospheric chemistry well enough to rule out abiotic processes. And we can't rule in biological processes without much more data. What we need is to go there, to sample the clouds directly, to measure chemical compositions in situ, to observe atmospheric dynamics and photochemistry in real time. Which brings us back to the fundamental problem. We haven't been to Venus in decades. We don't have the infrastructure. We don't have the missions. We don't have the data. Until now, in June 2021, NASA made an announcement that surprised the planetary science community. The agency had selected 2 missions for its discovery program. Both were going to Venus. Not one mission, 2 at the same time. The first is called Da Vinci Plus. Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging Plus. It's a probe that will descend through the Venusian atmosphere, taking measurements all the way down to the surface. The probe will analyze atmospheric composition, detecting noble gases, isotopes, and trace compounds. As it falls through the clouds, cameras will photograph the surface at higher resolution than ever before achieved. Infrared spectrometers will identify minerals on the ground below. The mission is designed to answer the question of when Venus lost its water. By measuring the ratios of different isotopes of noble gases, scientists can determine the planet's thermal history. When volatiles were released from the interior, when atmospheric escape began, whether Venus was habitable for billions of years or lost its oceans early. Da Vinci Plus will also study Alpha Regio, one of Venus's tesserae. These ancient highland regions may preserve evidence of a wetter past. If the rocks contain minerals that form only in the presence of liquid water, it would confirm that Venus once had oceans. If they're purely volcanic, it would suggest a drier history. The probe will survive for about an hour during its descent. Then it will hit the surface, and its instruments will fail. But that hour will provide more direct atmospheric data than we've collected in the past 40 years combined. The second mission is called Veritas, Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy. It's an orbiter with a state-of-the-art radar system, much more advanced than Magellan's. Veritas will map the entire planet in 3 dimensions. high-resolution topography down to about 30 feet per pixel, infrared spectroscopy to identify surface compositions, gravity field measurements to probe the planet's interior structure. The mission will look for active volcanoes, signs of recent lava flows, deformation in the crust that indicates magma movement below. It will study the tesserae in detail, determining whether they're sedimentary, volcanic, or something else entirely. Veritas will answer questions about Venus's geology that Magellan couldn't resolve. How often does volcanism occur? Is plate tectonics possible, or has the planet evolved through a different mechanism? What is the internal structure? How much heat is escaping from the interior? Both missions are scheduled to launch in the early 2030s, Da Vinci Plus first, followed by Veritas a few years later. Together, they will transform our understanding of Venus. But they're not alone. In 2021, the European Space Agency selected Envision, an orbiter mission that will complement Veritas. Envision will carry radar systems for surface mapping and spectrometers for atmospheric and compositional analysis. It will focus on specific targets, providing detailed surveys of regions of interest rather than global coverage. Envision will also carry a radio science experiment to measure Venus's gravitational field with high precision. This will reveal density variations in the interior, indicating whether the planet has a liquid core, a solid mantle, and distinct layers like Earth. 3 missions from 2 space agencies, all arriving at Venus within a few years of each other. This represents a fundamental shift in priorities. After 3 decades of neglect, Venus is suddenly back in focus. The scientific community has recognized what was lost during the years of Mars obsession. There are other missions in development as well. Russia's space agency has proposed Venera-D, a combination orbiter and lander for the 2030s. India's space agency is planning Venus orbiter mission, scheduled to launch in 2028. Private companies have begun exploring the possibility of atmospheric missions using balloons or floating platforms. The renaissance is underway. Sending missions to Venus requires solving problems that don't exist at Mars or anywhere else in the solar system. The fundamental challenge is survival. At the surface, temperatures exceed 450 degrees Celsius. Atmospheric pressure is 92 times Earth's. The atmosphere is corrosive. Sulfuric acid clouds will eat through most materials. Carbon dioxide at high pressure becomes a supercritical fluid, neither gas nor liquid, with strange thermal properties that make heat management difficult. Conventional electronics fail within minutes in these conditions. Silicon-based computer chips stop functioning at around 150 degrees Celsius. Solder melts, circuit boards degrade, batteries die, mechanical components seize, optical windows fog or crack. The Soviet Venera landers solved this problem through brute force. They built pressure vessels with thick walls and massive thermal insulation. They packed lithium nitride salt blocks inside, which absorbed heat through phase changes. They used simple mechanical instruments that could function briefly before failing. Even with all these precautions, the longest survival time was 2 hours. Most landers died much sooner. Modern technology offers new solutions. Silicon carbide semiconductors can operate at temperatures above 500 degrees Celsius. They're used in aerospace applications where extreme heat resistance is required. NASA's Glenn Research Center has developed silicon carbide integrated circuits that functioned for more than 500 hours in ovens at 500 degrees. Some chips continued working in simulated Venus surface conditions for 60 days. This represents a 100-fold improvement over conventional electronics, enough to enable missions that can operate on the surface for weeks or months rather than minutes. But silicon carbide electronics are still primitive compared to silicon chips. The complexity is comparable to 1972 era computers. You can't build a sophisticated rover or complex scientific instruments with this technology. Not yet. So surface missions remain limited. Landers will carry simple instruments, temperature sensors, drills to sample surface materials. The goal is not extensive exploration, but targeted investigation. answer specific questions, measure particular parameters, gather data that can't be obtained from orbit. Atmospheric missions face different challenges. The clouds are less hostile than the surface. Temperatures and pressures are manageable, but navigation is difficult. Venus rotates slowly, once every 243 Earth days, but the atmosphere rotates much faster. Winds at cloud level reach 360 kilometers per hour, faster than the strongest hurricanes on Earth. Any atmospheric probe or balloon would be swept around the planet in just 4 days. Maintaining control is nearly impossible. You go where the wind takes you. This isn't necessarily a problem, it just requires different mission design. Instead of rovers that move to specific targets, you use floating platforms that drift with the atmosphere. Instead of landing at predetermined sites, you descend wherever the winds carry you. Instead of long-term surface operations, you focus on atmospheric measurements and remote sensing. NASA has studied concepts for solar-powered aircraft that could fly in the upper atmosphere indefinitely. The idea is to cruise at 50 to 60 kilometers altitude, where the environment is relatively benign. Use solar panels on top and bottom of the vehicle, since Venus's high albedo means reflected sunlight from below is nearly as intense as direct sunlight from above. The aircraft would ride the fast-moving winds, circling the planet every few days. It would carry instruments to study atmospheric chemistry, cloud structure, and surface features using radar and infrared imaging. It could communicate with surface probes, acting as a relay for data transmission. Such a mission would be technically challenging but feasible, and it would provide long-duration observations that orbital missions can't match. The real bottleneck is cost. Venus missions are expensive because they require custom engineering solutions. Mars rovers can use commercial electronics with radiation hardening. Venus landers need completely different technology. Mars missions can leverage decades of experience and proven designs. Venus missions are starting almost from scratch each time. This creates a vicious cycle. Venus missions are expensive, so they're rarely selected. Because they're rarely selected, the technology doesn't advance. Because the technology doesn't advance, missions remain expensive. Breaking this cycle requires sustained investment. Multiple missions in sequence, each building on the previous one's successes. Standardized platforms that can be reused. Incremental improvements in components and systems. That's what happened with Mars. Early missions were expensive and risky. Many failed. But over time, costs decreased and success rates improved. Now, Mars missions are almost routine. Venus could follow the same trajectory. If we commit to going back, if we decide that answering fundamental questions about planetary evolution and habitability is worth the investment. The decision has been made. Da Vinci Plus and Veritas represent that commitment. Envision reinforces it. The question now is whether this represents a brief resurgence or the beginning of a sustained exploration program. The most profound reason to study Venus isn't about Venus itself, it's about Earth. And it's about the thousands of exoplanets we're discovering around other stars. Earth and Venus are nearly identical in size. Venus's diameter is 95% of Earth's. Its mass is 82%. Its density is almost exactly the same. Both planets formed in the same region of the solar nebula, from the same materials, at roughly the same time. And yet, their fates diverged dramatically. One became a lush biosphere, oceans teeming with life, continents covered in forests, an atmosphere that breathes, a climate that, despite periodic ice ages and warm periods, has remained broadly stable for billions of years. The other became hell. Understanding why these two similar planets ended up so different is one of the most important questions in planetary science, because it tells us what factors determine habitability, what conditions are necessary for life, what thresholds separate a paradise from a wasteland. And we're desperately trying to answer these questions for worlds we can't even visit. Exoplanet astronomy has revolutionized our understanding of planetary systems. Thousands of planets orbiting other stars, many of them rocky worlds like Earth and Venus. many in the habitable zones of their host stars where temperatures could theoretically allow liquid water. But we can only measure a few basic properties of these worlds: size, mass, orbital period, sometimes atmospheric composition, though only for the largest, brightest examples. We can't see their surfaces. We can't measure their detailed atmospheric chemistry. We can't determine whether they're habitable or hostile. We need a reference, a way to interpret the limited data we collect, a framework for understanding how rocky planets evolve and what signatures indicate habitability. Venus provides that reference. It shows us what happens when a planet passes the tipping point, when greenhouse warming becomes irreversible, when oceans evaporate and atmospheres transform into crushing blankets of carbon dioxide. If we understand Venus, we can recognize the warning signs in exoplanet observations. We can estimate which worlds are more Earth-like and which are more Venus-like. We can assess whether a planet in the habitable zone is actually habitable or whether it's a scorched wasteland with a misleading orbit. This matters for the search for life beyond Earth. If Venus-like planets are common, then true Earth analogues are rare. If the runaway greenhouse threshold is narrow and easily crossed, then habitable worlds are precious outliers. If Venus's fate was determined by subtle factors we haven't yet identified, then predicting habitability requires much more information than we currently have. But it also matters for understanding Earth's future. Climate models predict that Earth will eventually suffer a runaway greenhouse effect, not from human activity, but from the gradual brightening of the sunday. As our star ages, it grows more luminous. In about 1 billion years, solar output will increase enough to push Earth past the tipping point. Oceans will evaporate, the water vapor will trap heat, the hydrogen will escape to space, Earth will become another Venus. This is inevitable, but the timeline depends on details we don't fully understand. How efficiently does water vapor escape to space? What feedback mechanisms slow or accelerate the transition? At what temperature does the process become irreversible? Venus has already gone through this transition. Studying it tells us what to expect, how fast the change occurs, what the end state looks like, whether there are intermediate stages where life could persist in refuges before the final collapse. This isn't just academic curiosity. Understanding Earth's long-term future helps us appreciate the temporary nature of our current environment, the narrow window of habitability we occupy, the fragility of the systems that support complex life. It also provides context for evaluating shorter-term climate changes. Human-caused global warming is not going to turn Earth into Venus, not even close. The runaway greenhouse effect requires specific conditions that anthropogenic carbon dioxide emissions cannot create. But studying how greenhouse effects amplify and become self-reinforcing helps us model the climate system's response to perturbations. Venus teaches us what runaway looks like. Earth teaches us what stability looks like. Together, they define the boundaries of habitability for rocky planets. And we can only learn these lessons by going there, by measuring atmospheric chemistry directly, by analyzing surface compositions, by observing volcanic activity and atmospheric dynamics in real time. Remote sensing from Earth-based telescopes can only do so much. We need spacecraft at Venus, instruments in the atmosphere, probes on the surface, long-duration observations that track changes over months or years. That's why Da Vinci Plus, Veritas, and Envision matter. They're not just missions to another planet. They're investigations into fundamental questions about how worlds evolve, what makes them habitable, and where Earth fits in the cosmic spectrum of possibilities. These questions don't get answered by ignoring Venus for decades. They don't get answered by focusing exclusively on Mars because it's easier to explore. They require sustained, systematic study of the planet that became our opposite twin. After 30 years, we're finally going back, but it's not enough. 3 missions will provide tremendous new data, but they're only the beginning. We need a long-term exploration program. Multiple orbiters, multiple landers, atmospheric probes and balloons. sample return missions that bring Venusian materials back to Earth for detailed analysis in laboratories. We need Venus science to become routine, not extraordinary. To have missions launching every few years, each building on previous discoveries. To develop the technology and expertise necessary for sustained exploration. Mars has taught us how valuable this approach can be. Decades of missions have given us a comprehensive understanding of that planet's history, geology, and potential habitability. Venus deserves the same level of attention, because the questions Venus raises are just as important, perhaps more so, given its similarity to Earth and relevance to exoplanet characterization. There is a planet hanging in our sky that we have almost completely abandoned. For 30 years, we chose Mars over Venus, chose ease over importance, chose the familiar over the challenging, chose the search for microbial fossils in ancient lakebeds over understanding how our twin world transformed into hell. This wasn't entirely irrational. Mars is easier to explore. The engineering challenges are manageable. The probability of finding past or present life, while small, is non-zero. And there's genuine scientific value in understanding Mars. It's a legitimate target for investigation. But Venus matters more. It tells us about Earth's future, about the stability of habitable climates, about how common Earth-like worlds really are in the universe. We lost time, 3 decades of missions that could have been flown, 3 decades of data that could have been collected, 3 decades of advances in understanding planetary evolution that we delayed because we looked away. The consequences are real. We still don't know when Venus lost its oceans. We don't know whether it was habitable for billions of years or died quickly after formation. We don't know whether the tesserae are ancient continents or volcanic plateaus. We don't know if volcanoes are currently active. We don't know what's producing the phosphine and ammonia detected in the atmosphere. All of these are answerable questions. All would be resolved by missions we chose not to fly. But the tide has turned. Da Vinci Plus, Veritas, and Envision represent a new commitment to Venus exploration, a recognition that we made a mistake by abandoning this world for so long. The missions will arrive in the 2030s. They will map the surface in unprecedented detail. They will measure atmospheric compositions with precision we've never achieved. They will probe the interior structure and search for active volcanism. They will study the tesserae and determine their origins. And they will undoubtedly raise new questions. Every mission to Venus has done so. The more we learn, the stranger it becomes. The atmosphere is more complex than models predict. The surface is younger than it should be. The chemistry doesn't behave as expected. Venus is not a solved problem. It's a mystery that deepens with each new observation. Perhaps that's why we turned away. Mars is comprehensible. Its history is mostly written in stone, waiting to be read. Venus is chaotic, hostile, and confusing. It resists easy understanding, but science isn't about studying what's easy. It's about studying what's important. And few questions are more important than understanding how Earth-like planets evolve, what determines their habitability, and where our own world sits in that spectrum. We're going back to Venus because we have to, because the questions demand answers. Because 3 decades of neglect was long enough, the next chapter of Venus exploration is about to begin, and perhaps this time we won't turn away. Perhaps we'll commit to sustained investigation, building the knowledge base and technology foundation necessary for truly understanding our mysterious twin. Perhaps we'll finally give Venus the attention it deserves. The planet waits, unchanged and patient, wrapped in clouds of sulfuric acid, hiding secrets that could reshape our understanding of worlds throughout the universe. It's time to go back. What we know so far is fragmentary, pieces of a puzzle scattered across decades of sporadic observation. The Soviet landers gave us brief glimpses of the surface. Magellan mapped the terrain, but couldn't explain its youth. Atmospheric observations detected unexpected chemicals, but couldn't determine their source. Every answer has brought more questions. Da Vinci Plus will descend through the atmosphere, measuring compositions and photographing the surface. Veritas will orbit for years, watching for volcanic eruptions and mapping every tesserae. Envision will fill in the details, targeting specific features with high-resolution instruments. Together, they will tell us when Venus died, how quickly it transformed, whether it was ever truly habitable, what processes shaped its surface, whether life could exist in its clouds. But they won't answer everything. No 3 missions could. Venus will remain mysterious, still strange, still resistant to simple explanations. And that's as it should be. The universe doesn't yield its secrets easily. We learn through patient observation, careful measurement, and sustained investigation. We walked away from Venus for 30 years. That was a mistake. But mistakes can be corrected. We're going back. Not because it's easy, not because it's popular, but because understanding Venus means understanding Earth. Understanding what makes a world habitable. Understanding what we risk losing if we're not careful. The missions will launch in the coming years. They will arrive at Venus in the 2030s. And for the first time in decades, we will watch as new data streams back from our forgotten twin. The planet that became hell will finally tell us how it died. And in doing so, it will teach us how to recognize life when we find it elsewhere, how to protect it here, how to appreciate the narrow circumstances that make Earth, for now, a paradise in the void. Venus waits in the sky, patient, eternal,